In this lesson, we introduce the concept of current and discuss the drift speed of electrons. Here are your objectives. First, current is defined as the flow of charge, and it's given the symbol I, and its units are amperes, and amperes are given the symbol A. 1 ampere is defined as 1 coulomb of charge passing a given point per second. In formula terms, I is equal to delta Q over delta T, the amount of charge passing a given point per unit time. Now, when we talk about conventional current refers to the flow of positive charge for historical reasons. But of course, we don't want to wire what's really moving are the electrons. Conventional current moves from high potential to lower potential. High potential to low potential means that the conventional current is moving from the positive terminal, for example, of a cell round a circuit and then back in at the negative terminal. The electrons are actually moving in the opposite direction. The electrons in a conductor, which we might call the electronic current, move from low potential to high potential. So they're moving from the negative terminal of a cell around the circuit and then into the cell at the positive terminal. If this is our wire, and this is the negative end closer to the negative terminal of the cell, and this is the positive end closer to the positive terminal of the cell, the conventional current is moving in this direction, but the electrons are actually moving in that direction. And again, the reason that we talk about conventional current at all is because before electrons were discovered, it was thought that it might actually be positive charges moving in these wires. And mathematically, pretty much everything works out exactly the same, whether it's positive charges moving to the left or negative charges, electrons moving to the right. And because a number of the other aspects of electricity are worked out based on conventional current, we'll use that a lot of the time. Just remember that what's really moving are the electrons. Now let's zoom in closer and take a microscopic view of what's going on in the wire. Remember that metals consist of positive nuclei surrounded by a sea of delocalized shared electrons, and it's those electrons that can move and carry charge, a current. With no potential difference across a wire, those electrons are moving rapidly, but they're moving randomly. They're just bumping around in all direction, and they have no net displacement in one direction or the other. When there's no potential difference, they're just bumping around. This is very much like the molecules in a pipe full of water are moving, they're bumping around in all directions, but they're not flowing through the pipe. You can tell that they're moving because if you were to drop food coloring into the water, that would spread out, and that's because the molecules are bumping into each other, but the water is not flowing through the pipe. Very similar kind of thing happening with the electrons. The electrons are moving very fast, but not with any net displacement in any one direction. However, if you apply a potential difference from a battery, then the electrons are going to experience what you might think of as a kind of pressure. It's like putting a pump on one end of your pipe full of water, or tipping one end of the pipe full of water up. So the electrons experience a kind of pressure, and their net movement, therefore, is towards the positive end. So if we think further about this wire across which we've applied a potential difference, here are my negative and positive ends, so my electrons are moving to the right as a result of the potential difference I've applied across it. We can actually work out what the drift velocity of these electrons is. So that's not the same as their bouncing around velocity that they were doing even in the absence of a potential difference. It's their net movement, their net velocity towards the positive end. So we're going to let v be the average drift velocity of the electrons as a result of their net movement towards the positive end. Delta t is their elapsed time. A is the cross-sectional area of this wire, like that. And n is the charged particles per unit volume, and q is the charge on each particle, which we'll use in a moment. So we're going to use these variables and this idea to work out just how quickly the electrons are moving towards the right. So if we have a cylinder like this, then if the electrons are moving to the right at speed v, then in a time delta t, the length of this cylinder is just the speed that they're moving multiplied by the time we allow them to move. The length of the cylinder through which the electrons will move in a time delta t, again, is equal to v delta t, because length is equal to speed times time, or distance is equal to speed times time. The distance they move is their speed multiplied by the time we let them move. So that's the length. The volume of a cylinder is equal to its cross-sectional area multiplied by its length. So if this is the length, I multiply cross-sectional area by the length, and now I've got the volume of that cylinder. If I wanted to find the number of electrons in the cylinder, I need to take the volume and multiply by the number of charged particles per unit volume. And that's n in our definition. So the number of electrons in the cylinder is the number of electrons per unit volume multiplied by the volume, and we've said the volume is AB delta T. Now, if we want to find the total charge in the cylinder, we know the total number of electrons. That's what this expression is. So I multiply the total number of electrons by the charge on each electron, which we've defined as Q. So the total charge in that cylinder is equal to this expression. And if we wanted to find the total charge passing an observation point in a time delta t, so let's say, for example, we were watching here and we wanted to find out how much charge is passing us per unit time delta t, well, we've got the total charge in the cylinder, and we've said that whole cylinder is passing us in a time delta t, so we just divide NAV delta t q, divide out the delta t's, and those are going to cancel. So the charge moving past any point per unit time is equal to n times a times v times q, with these variables all defined as above. The charged particles per unit volume, the cross-sectional area, the drift speed or the drift velocity of the charged particles, the electrons, and the charge on each of them. Now, the charge moving past any point per unit time is our definition of current. So the current is equal to n times a times v times q. And that actually would allow us to solve for the drift speed, the drift velocity, if we wanted to. In other words, the drift speed is equal to the current divided by n times a times q. So if I knew all of the others, I could work out the drift velocity. And it actually turns out that that's quite slow. The electrons are only moving to the right at a speed on the order of, let's say, about 1 meter per hour. It's going to depend on what the current is, the cross-sectional area, etc. But it's pretty slow. It's a common mistake to think that because when you switch a light switch on, the light goes on immediately, that means the electrons are moving very fast. The electric field is propagating through space very, very quickly at the speed of light, but the electrons themselves are moving rather slowly. And in fact, in an alternating current circuit, like the ones in your house, the electrons are just moving back and forth, oscillating. They're not actually progressing towards the light at all. So that's an introduction to the definition of current, and also a look at the drift speed of electrons in a wire.